just brought up the star field.
First Monday.
This is the star field for those of us who will be in the path of totality. So, this is the eclipse sun. This is Regulus. It might actually be hidden in the solar corona. The planets visible will be Mercury, off to the left and a little bit down, and Venus, very bright, and Mars here. So the star field is going to be Cancer, which is very unimpressive, Sextans, no comment, and the remainder of Leo, including the very nice double star Algeba. So this is what you will have time, and I certainly will be doing it myself, take a quick look around to see if we can pick up Mercury, Regulus, Algeba, Mars, Venus, and forget about Sextans.
Yeah. Question, which way is the moon coming from again? From the right? So what I'm wondering is how quickly is Venus going to disappear from the dark part of the sky? Because this simulation does not actually simulate the moon shadow.
No, it doesn't.
So Venus is going to disappear from the moon shadow at some point, and I want to know if I need to look at it first.
All right, so Venus.
Is it coming from the east or is it coming from the west? I should know this just okay. So it is.
The shadow is coming from the west.
So the shadow is coming from the west.
Yeah,
So
it's moving east.
so Venus will only get better over the course of the eclipse, right? The shadow will come from the west.
Yes.
So the moon comes from the east.
No, the moon is coming from the west.
Oh, Christ.
Well, wait. So if the moon is coming from the west, then the shadow should be cast to the east, right?
Eastward, yeah. So the shadow also comes from the west. Going eastward.
Going east.
Yeah, the moon.
Like, I mean, which direction will the shadow be in the sky? Because the shadow moves, right?
Yeah.
Somewhat.
It should come from the west, moving eastward.
The shadow on the ground is from west from west.
No, I want the shadow in the sky. I want the dark part of the sky.
Same thing.
Okay.
What's covering the sun, you mean?
Yeah, I guess that
Again,
makes
going
sense.
from the right to the left.
Okay, that makes sense. Yes.
There it is,
Okay.
there is a 1250 and it's coming.
So you
Oh, it's
lose
coming from the
Mercury
right to the left,
first,
right.
and then Venus.
Pretty cool. The Stellarium does that. That's
Now,
pretty
where was
cool.
Venus in there?
Way over
Venus
to the right.
is way over to the
it's way
right.
over- Oh, I'm sorry. Okay.
It might be a challenge, but it will be.
Oh, I
right,
see.
so-
Oh, I got you. Okay.
It'll be basically sunset, so it probably should pop out even in sunset. What scale is this? Is this about true scale?
Depends on where you're sitting.
Well, I plan to sit on Earth.
Why is the Earth sunlit from the sky?
Light pollution. I think Venus should be in the moon shadow. I guess we'll find out for sure. Somebody will find out for
Bring it
sure.
up, 'cause that's pretty cool.
Venus is so bright, there will be no problem seeing it, unless you got high haze.
Might have high haze. I was looking at the forecast for Nebraska today.
Yeah? What?
What is the weather forecast for Monday?
I don't know for anything other than Nebraska.
What's the story?
10% chance of
So far,
precipitation.
sunny, yeah, clear, I think.
And it looked like
That's not what I heard.
their illustration showed what appeared to be a high, their artist rendition showed high
No,
haze.
I'm staying here.
Or sort of a tenuous something up there. All right, so this is part of the night that I turn things over to our program chair, Mark Kedzier, to introduce our speaker.
Thank you, Madam President.
Let's make sure the camera's rolling.
Is it rolling?
Are we rolling?
5, 4,
Yes. Take it away.
Okay, here we go. I want to thank, first of all, Mr. Trembley for doing this presentation. I guess we just can't get enough of the sun this year. But let me say that even with Ken Burton, he knows a little bit about eclipses. But every little bit that's helped has helped me actually in my outreach doing over at Grosse Pointe. The people are just thrilled with this stuff and everything, so this is really exciting. Mr. Trembley he got his first telescope in the year 2000, I believe, right? He got a PST, an 8-inch Orion Dob, and you watched the solar eclipse in Christmas Day 2000. I did also. That was pretty awesome there too. Bob and his wife Connie are very avid into outreach, doing astronomy and space lectures, and we always read all of his outreach events, and I really admire Bob with all of his, what do you call this stuff, his technical wizardry with his presentation, so I always enjoy it, so it's really good. So without further ado, Mr. Bob Trembley is going to be doing his expanded version of his famous sun lecture. Take it away, Bob.
All right, Just kill him?
Kill him.
Alright. Alright, so yeah, I'm Bob Trembley. I've been an amateur astronomer since I was 8 years old. That's my job and my PST that I got in 2000. I actually had a refractor when I was 8, but that thing died when I was a teenager. So I am, come on. Right again. Alright, I'm the outreach officer for the Warren Astronomical Society. I schedule our volunteers to do things like this, talk at schools and things like that. And I am a volunteer NASA JPL Solar System Ambassador. It's a really cool program where NASA recruits people to do a lot of astronomy outreach, and we get to we get to sit in on teleconferences with mission specialists, engineers, scientists, and get the latest scoop on what's going on, and then do outreach for NASA. Essentially, I'm a volunteer NASA cheerleader, and so are 3 other members of this club. So yeah, I'm a solar observing enthusiast. This is me and my PST. This is me giving an older version of this lecture at my wife's 3rd grade classroom. And so yeah, the sun. When most people think about the sun, that's what you got, right? Okay, well, it's a little more exciting than that for me. I did this to the 3rd graders, you know. I said, "What's the sun?" And they're all, "A star." That's right. Great. What's a star? And I hear crickets. Crickets, they need a sound effect for that. But so yeah, the first thing I asked them, "How big is the sun?" And they're like, "Bigger than the Earth?" Well, yeah, okay. But it's 865,000 miles across, nearly, you know, the better part of 1,000,000 miles across. And there's the Earth down there compared to the sun. So you can see it's pretty dinky. You can fit 109 Earths across the face of the sun. Remember, the sun's a big sphere, so you can fit 1,000,000 Earths in the sphere of the sun. So it's pretty darn huge. Now, this is actually a trick question. Nobody ever gets this right because there's a lot of zeros there. So let's relate it maybe to something you can relate with. It's 333,000 times the Earth's mass. Yeah, that's pretty darn heavy. So what's really, really cool, if you took everything in the solar system out to the Oort cloud, summed all that mass together, the sun would be 99.86% of that mass. Everything else is 0.14%. I tried to do this as a pie chart. The line, it was just a line. So you couldn't even tell there was a pie slice there. So of this 0.14% that makes up everything else in the solar system, most of that's sitting in Jupiter. So when you're talking about the solar system, you're talking about the sun, because it's pretty darn heavy. So how far away is it? Everybody knows this, 93 billion miles, takes like 8 minutes to reach us. What's the sun made out of? It's amazing how many kids actually get this right. Some of them don't get gas, they don't know what kind of gas, but I've actually had some kids actually get both of these right. And the fact, you know, it's mostly hydrogen, a lot of helium, and 1% pretty much everything else in the periodic table. And all in a state of incandescent plasma. Great. What's that? Well, incandescent means it's emitting light because it's hot. Well, okay, yeah, that's the sun. And plasma is not one of these. It's, well, you're probably familiar with one of those, right? That's plasma. Only it's not quite as hot as the sun, but it's an ionized gas. It's electrically conductive, and it responds strongly to, gosh darn it, really sensitive. Responds strongly to magnetic fields, which is going to be very important when we talk about the sun. So here's some other examples of plasma. Lightning, you're probably familiar with. Some of you may have seen Aurora, those interesting clouds of gas and dust, the sun. Those are all examples of plasma. So the sun, the core of the sun is about 25% the radius of the sun. And this is really interesting. It's 10 to 15 times as dense as lead, but it's plasma. Yeah, that's just crazy to think about. And now you guys have swum to the bottom of the pool, maybe felt the pressure pushing in on you. That's what, 1.5, maybe 2 atmospheres? The core of the sun is 100 to 350 billion atmospheres. It's really hot, and it's undergoing fusion. Now this is a really interesting process. This is what my buddies say the sun is. So this is the proton-proton chain fusion reaction. Essentially, long and short of it is, hydrogen comes together and you end up with helium. It releases a whole lot of high-energy photons and a whole bunch of neutrinos. This is for larger stars. This is the CNO cycle, the carbon, nitrogen, oxygen cycle. We're not going to go into that, but just be aware there are other cycles going on. So in the sun, 600 million tons every second gets converted into helium, and that leaves a little bit, so, E equals mc squared, you got to conserve that, so 4 million tons gets converted into energy. Most of that energy is gamma rays, but a lot of it are neutrinos. Now, neutrinos are really weird. They hardly interact with anything. They can travel through like a light year of lead and never touch another core of an atom or anything like that. That's the flux at the Earth's surface. 100 billion neutrinos in every square centimeters every second. So anybody care to, how many square centimeters are in a sphere 1 AU around the sun? That's a lot of neutrinos. So that's the fusion reaction going on in the sun. And that process is called nucleosynthesis, and that's the process by which heavier and heavier atomic nuclei get created in stars. We'll be going into this a little bit later. So, yeah, Carl Sagan, he's one of the first person that introduced me to this fact that all these elements that get created in stars, well, they're right here. So that's really interesting. So when these photons get created, okay, the neutrinos, they just come screaming out of the sun in all directions. The photons, I remember it's 15 times as dense as lead, they get about that far before they smack into something, get reabsorbed. So they go on this crazy random walk, and it can take thousands to millions of years before they finally get out to the photosphere of the sun and get away. Now the sun is in a state of hydrostatic equilibrium. You've got, well, it's heavy, right? It's got all this, it's massive, so it's got all this gravitational force pulling in, and you've got gas pressure and fusion pressure pushing out, so it just sits there. That's called hydrostatic equilibrium. And when those photons reach the surface here, that's when they get out. The photosphere of the sun, that's the depth which the light finally gets out. But it's not solid. It's very, very low density. So there's really no surface to the sun, and this part of the sun is it's 5,000 degrees. You go a little deeper, the temperature starts really going up. I love this. This is the surface of the sun with time exposure. These are called granules. And the biggest one of these things is about the size of the state of Texas. And I had one kid actually ask me, what's that white area down there? Well, actually I had to look that up. Actually, because we have to label everything, that's called a facula. That is, it's a magnetic region that's probably where a sunspot is going to be forming. And this is on the photosphere. So, these are the granules, and you've got, it's almost like boiling soup. You've got, or a lava lamp. You've got the plasma comes up, cools down, goes like that, and it's very turbulent. So the sun, big ball of gas, not solid, it rotates differentially. The equator rotates faster than the polar and upper latitude regions. And what happens is that takes these magnetic field lines and bends them all around in the sun until you get a mess like that. And this is happening all the time on the sun. So sunspots, this is a picture of sunspots. These are essentially magnetic storms. And what you've got is these magnetic field lines coming straight down here. There is a sunspot. The dark part's called an umbra. These are called penumbra. Now these are granules again. These are granules too, but they're being stretched by that magnetic field line coming in there. They generally come in pairs, almost like a positive and negative. And what's happening is it's preventing this convection, so that area is cooler under there by about 1,000 degrees. If you took a sunspot and put it out in space by itself, it'd still be really, really bright, but it's darker than the stuff around it. So there is a time exposure of a sunspot. Yeah, it's really, really cool. Very mesmerizing.
What was this taken with, Bob?
Pardon? This was taken with previous. actually European Southern Observatory. Oh God, it's a solar telescope on an island off Africa. I can't
Canaries?
remember.
Canaries.
Canaries.
I
Yeah.
can't remember the name of it.
Where are the hobbits right now? In
Yeah.
So
Let's
this,
follow us.
this is a particularly really cool sunspot. This picture was taken by Alan Friedman and Randy Shivik. Randy Shivik took the image, and Alan Friedman, who's been doing a whole lot of really cool pictures of the sun. He processed that. This was a couple of years ago, and that's just absolutely beautiful sunspot. That was much larger than Jupiter. Very, very cool. So that's the sunspot you just saw. That is in a different frequency. So you can see this is the active region. This is like ultraviolet. So there's a lot of activity going on, and that's what you see in visible light. So pores are small sunspots. They don't generally have this this penumbral part of them. They're baby sunspots. Sometimes they'll grow into larger sunspots. Now the sun has an 11-year cycle. It has a heartbeat, essentially. And what it does is it goes from a whole bunch of solar activity down to none, and it goes a loop every 11 years. We came off solar maximum just recently. We're probably around here right now in activity-wise. And this is seeing the sun probably hydrogen alpha frequencies. This is the corona. You can see again, hardly any activity to a lot of activity, and the loop goes every 11 years. This is pretty much a summation of 3 years worth of activity. You can see the sunspots generally, and the active regions generally tend to stay in those bands there. So, about 400 years ago, we had this minimum where for several cycles there weren't any sunspots at all, and we haven't seen anything like that again, and we don't know why it happened, and we don't know if it's going to happen again. Could it be another cycle, longer cycle we don't know about? Maybe. We've only been observing the sun for about 400 or 500 years now. That's it. So, is it going to happen again? Who knows? Now this is again Alan Friedman. These are his images. The chromosphere on the sun sits a few thousand miles up from the photosphere, and some interesting things live in the chromosphere. Now, these things are prominences, and Marty described them as clouds in the sun's atmosphere. I kind of like that. But they're clouds of plasma. They hang out. They can be rather big, as you can see. They can be small. Because we have to label everything. They all have names. My favorite is the hedgerow. I've seen several of those. I like those a lot.
Broken.
So there's a disconnected to show you example of some, and this is the limb of the sun here down here.
Oh, yes.
The loop. That's really cool.
Is
The
that
double loop.
1946?
Really?
yeah.
Really?
That's what it said.
I like that one. My wife calls that a phoenix. I think that's pretty cool. But here's time exposure, and and you've got several different ones here. There's a pyramid down there that's pretty much just hanging out there. This one is disconnected and is flowing off. So this is going on all the time on the sun. Now again, this is the limb of the sun here, and you're looking at the blackness of space here. So you're seeing this from the side. If you saw this down from the top, it would look like that. That is called a filament. They appear in on solar telescopes as this black, like a black crack almost, and if you Photoshop the heck out of them, they look like that. So, I think this is pronounced plage. That is a bright area around sunspots. This is its counterpart is the facula. So you have a sunspot with a facula around it and the photosphere, and then up in the chromosphere, you've got the plage. They're kind of on top of each other.
Beach.
Pardon me?
In French. Beach.
Sur l'épave, le plage.
Anyway, I took this picture with my solar telescope, and that was pretty cool to see. So these are specules. These are like, think plasma hairs on the sun. They're half as wide, or as wide as a state, long as the Earth's radius, and they just sit here and they flow really quickly and they dissipate like that. There is a really, that's really cool. I love that picture. Almost looks like fur.
Yeah.
Hot plasma fur that you don't want to pet. So a corona out from is an aura of plasma, and so it surrounds the sun. It can go out. It can have streamers that go out for millions of kilometers. Some of you are going to be able to see that on Monday, hopefully, rather than clouds. That's what you guys are going to see on Monday. We're going out there. And what's really cool is to see, you can see the magnetic field lines coming out of the sun. Essentially, what you got there is a big bar magnet. And this is the corona of the sun in ultraviolet. You can't see this. Well, with your eyes, you need a space telescope to see that. This is another flavor of ultraviolet, and what you're seeing, all these loops are in the active region here. Those are called coronal loops. And what you've got here is plasma flowing along the magnetic field lines. And again, this is all over the sun, all the time. There's a sun in there is coronal loops on an active region. Sunspots are called active regions. They all have names, AR, and then a 4-digit number right now. So this was really cool. This is called coronal rain. What happened here is there was a flare right here, and then this giant loop formed going way out into the corona, and that is sucking plasma out of the corona. That is literally hot plasma rain on the sun. So does it rain on the sun? Well, yeah, it's just not wet and annoying like it is here. It's just hot and annoying. So these are coronal holes, and we have one of these today, as a matter of fact. I'll be showing you pictures of that. These are areas where the magnetic fields have opened on the surface of the sun, and solar wind has been known to stream out of these things. Speaking of solar wind, here's Comet Ison coming in 2013. You're going to notice that's a coronal mass ejection. Notice the wind just constantly streaming out of the sun here. This is taken with the SOHO space telescope. This is the sun right here, and it's blocked out by this occulting disk. So you're seeing the corona, much like an eclipse does. But what you're seeing is Comet Ison whipping around the sun there and disintegrating. You're seeing coronal mass ejections and stuff just spewing out of the sun. Again, this is going on all the time on the sun. Here's another comet going by. SOHO's taken thousands of pictures of comets whipping by the sun, but you can really see the streams coming out of there. So a flare on the sun, unlike a prominence, a flare is a quick release of energy. Enormous amounts of electromagnetic energy get thrown out into space really, really quickly. And flares have classifications. I'm not really going to go into that much, but they're like almost like a logarithmic scale until you get up to X, we've seen X28 flares. Can they go larger than that? Well, we've seen X28 flares. We don't know. So you guys have seen these things, right? Balsa wood airplane. Think that rubber band in there is like the magnetic field lines on the sun. And if you're twisting up that magnetic field line twists around, eventually it's going to kink. That's your prominence sticking up through the surface of the sun. If you keep twisting it and keep twisting it, you're going to build up a lot of energy. Eventually that thing's going to break, snap, come hit your hand, hurt. Well, that's a flare. It releases all that energy at once, and typically what it does is it pulls a lot of stuff off the sun and spits it out into the solar system in what's called a coronal mass ejection. These things release, these things are magnetic fields and particles, and this happened in 1859. Actually, I think Dale went over this. I'm just going to go over it really, really quick. In 1859, the only way we could observe the sun was in visible light with filtering. They didn't know about hydrogen alpha. They didn't have that. They didn't know about coronal mass ejections. They could see sunspots. Well, this Carrington fellow saw like a crescent, very bright crescent in a sunspot. I've seen this in my solar scope. It's really, really cool. Well, it was a really big flare, and he thought it was a flare. They recorded it. He didn't know about the giant coronal mass ejection heading toward the Earth. Well, this thing hit the Earth within 18 hours. Usually they take like 2-3 days. This thing hit after 18 hours, and it just did crazy stuff. People were waking up at 3 a.m. in the morning because the aurora was so bright they thought it was daytime. There was aurora from Pole down to Jamaica. The only electrical infrastructure at that time was telegraph, right? That was it. Well, telegraph machines were catching fire, exploding, and the weirdest thing I've heard is one of them kept running after they unplugged it. So, and these events happened a couple times and they started to realize at that time that maybe the sun had a magnetic component and they started learning a lot. But, again, 1859, telegraph, right? What would happen if the same thing happened today? Well, here's an apocryphal picture of dead cars on the road and power lines going crazy.
Not pictured, all the power transformers frying.
Yes, imagine that. Now, NASA estimates that there's a 12% chance between 2012 and 2022 of a Carrington-like event happening again. And are we prepared for that?
Well, yeah, but facing what direction?
It has to come and hit us, not glance us, as happened in 2012. Speaking of Carrington-like events, there was one in 2012, but it didn't hit us. It just grazed us a little bit, and it did cause a geomagnetic storm, but not
Missed
powerful.
opportunity.
In August, there was this guy. And this is really cool because, yeah, this is a flare, caused this, and you can see the shock wave traveling across the sun and stuff. But, yeah, there's the Earth wind scale to that. So that was a huge flare. That is what got spit out into the space from that. So that was very, and it glanced the Earth, causing aurora, but that's about it. Now what happens is these CMEs, these huge masses of particles, they can hit the Earth's magnetic field, and they can spiral down this way, and they can also cause the magnetic field to bend. Something, the field lines can come together back here and snap, energy can come back up. But the end result of that is it causes aurora around both poles. And there's the aurora from the International Space Station. Really cool. This is what it looks like. Real time I've seen this. They can move that fast, or they can be really slow, and they can dome overhead. They're just amazing. This is a picture of the aurora I took in Chesterfield, a block from my house in 2011, so you can see them down here. I've seen it 5 times since I built my house down here. But again, you gotta really look for them. So, and speaking of looking for them, you can go to spaceweather.com, and they have this thing called, they have an aurora notification. This is an auroral oval. That's an estimate of where you're going to see the aurora. So if you want to get an estimate, am I going to see it tonight? Spaceweather.com. They have an app that you can sign up for, and there's an aurora notification app for smartphones that tells you what the likelihood of seeing aurora. Speaking of aurora, that solar wind goes out into the solar system, and we've seen aurora on Jupiter. That's ultraviolet, actually. Saturn. And I found this out as I was updating this lecture.
Yeah.
Uranus and Neptune, they both have aurora, and they're both related to the magnetic field, but the magnetic fields on Uranus and Neptune are crazy. There's a quadrupole component to it. Yeah, so this is something that somebody else can do something on, but there's aurora on Uranus, and this isn't Neptune, but Neptune has type B auroras, which they would expect it to have type A, but it's mostly they see type B. That's type B on Earth. So we've seen them on Neptune. Now, the sun rotates, and when it belches out these coronal mass ejections, they spin out into the solar system like this, like that. So they fan out in these weird spirals. And the solar wind keeps going out until it hits what's called the interstellar medium. At this point, well, the best way to see this is you've actually seen this yourself. This is actually the tail. Here's your sink, right? Okay, so let's say that is the sun. That's where all of the energy is coming. You have the solar wind streaming out. Eventually it's going to hit the interstellar medium, and start slowing down, rumpling in, flowing back. This is your tail, and this is taken by the ibex. That is the tail around the sphere. So the solar wind comes out and flies back, and there's actually a really interesting article about this on the ibex site about the type of particles and how they discovered it. Again, somebody could do an entire lecture on just that.
That round thing, is that the Earth I'm looking at?
No, that's
You know, on the right.
previous Sun, Heliosphere.
Ah, oh, all
And
right.
this is the helio tail,
Fine.
is what it's called. Yeah, so
Fine.
we're talking huge here. All right, so you got that. And the sun's gravitational influence goes out to about a little over 1.5 light years. It holds all these things in the Oort cloud, so it goes way out. This is a logarithmic scale. So the sun's gravitational influence goes way out past its magnetic influence. And there are several space probes out there that are watching the sun constantly. This is one of Ken's favorites, SOHO. That's the one with that occulting disk, and it sees all the comets going by and the coronal mass ejections. That guy has been up there for a long time. Its missions has been extended over and over and over, and it's just a fantastic mission. It is located at the Earth-Sun L1 point, so it is in the station keeping orbit between the Earth and the Sun right there. Iris, this is looking at the interface region right here. So it's looking at how flares get created in the interface between the photosphere and the chromosphere. IBEX, that is the guy that gave us that information. And it's looking at the particles in the magnetotail and detecting those.
How far away is something like that?
Oh, IBEX?
IBEX.
I can bring it up and show you.
Million miles.
I think it's Earth orbiting. I'm not sure. I can find out for you.
The
SDO, this is my
Well, I was
favorite.
asking about his IBEX.
Oh, sorry.
This is my favorite. I love this probe. Solar Dynamics Observatory lets you, I was showing you at the beginning, it lets you see the sun in all these different frequencies right now, 48-hour movie, and you can also, it also has a data feature where you can go in and get whatever you want from the entire time it has been in space and generate a movie for time frames. It's really, really cool. It allows you to do things like this. Again, for instance, this is almost like hydrogen alpha. You can see magnetic field lines here, and zoom in, get in like that. This is the corona. This is today. I went and got these right before I came here, so that large sunspot group you're seeing. There's hydrogen alpha. You can see it's a very active region with a huge prominence down here. Corona. One flavor of corona, active region. Another flavor of corona. You can see we have a huge coronal hole right now. And this is a combination of several different frequencies. So stereo, this is two space probes that are orbiting essentially on the opposite side of the sun from us. So we've got 3D coverage of the sun. We actually lost stereo B for a while, but they regained control of it, so yay. So this is how they're orbiting. This is the Earth here. This is where these two guys are orbiting. So when it has coronal mass ejections going the other way, we can see them now. So that's pretty cool. This guy, its primary mission is not actually to observe the sun. It's to map the Earth, and it takes pictures of the Earth like every 15 minutes. But it has equipment to look at the sun. So, and this, I'm sorry Parker's not here. Solar Probe Plus, this is a mission to go through the solar corona. It has since been renamed from the Solar Probe Plus to the Parker Solar Probe, and that's going to be its orbit. Closest approach is going to be 4 million miles, and it's going to use 7 Venus gravity assists, and it's going to orbit for 24 times between 2018 and 2025, so that's going to be a very exciting mission. For those of you on Facebook, there is a solar activity group run by another solar system ambassador. These are amateur pictures that were posted yesterday using telescopes that you can get. So those are pretty amazing, and there's just tons and tons and tons of really cool pictures of the sun on that. So some of you may have heard that this is going to be happening on Monday. So I've got an application that I got this from NASA Eyes on the Solar System. It has a web-based component that lets you view all sorts of stuff like this for the eclipse. This is the path the eclipse is going to take. This is what we're going to see in the Detroit area. We're going to be covered about 76 to 80%, something like that. So that's what we're going to see at max. Right there is what we're going to see. And for those of you going elsewhere, you're going to be able to see that. Now, yeah, this is the obligatory, don't look at the sun closely, because you guys might have fried ants or something like that when you were a kid, whatever. Magnifying glass, right, focuses the light down, gets very, very hot. Well, your eyeball does the same thing. And the back of your eyeball doesn't have any pain receptors, so it will gleefully fry the back of your eyeball, ruining it. Don't do that. Use the right protection. Solar glasses, if you've got solar filters for telescopes, and this is a custom telescope meant to look at the sun. NASA Eyes on the Solar System, this is an app, I can show you this later. This is a free app, so just think Eyes, NASA, and you'll find it. It has a whole bunch of different modules. You can do Earth climate data. You know, see the solar system as it is right now. It's got tours for all the different missions. Exoplanet data. You can see all these exoplanet systems they've discovered. They're modeled in here. You can go to them, see them, compare them to our solar system. And it's got this eclipse thing built into that as well. So you can use that as a utility. So here's some of the other stuff you can do and NASA Eyes. So I can't say enough good things about this app. So yeah, again, this is what we're going to see from Michigan. And we're going to have people, oh, I didn't put one in here for Mark. I'm sorry. We're going to have people at Cranbrook. I'm going to be at Brandenburg. And Mark Kedzier is going to be at Grosse Pointe Woods, right?
Yes, sir.
Yes. So
Woods Branch Library.
Pardon me?
Woods Branch Library.
Wait,
So-
And two libraries.
Yeah, and
Right, and
Ewald.
also the Ewald branch.
Ewald
Ewald.
Branch.
And that's
So-
right off of Jefferson.
This is usually where I've stopped. Actually, this is a lot longer than I usually give at Stargate for the kids. I've added a bunch of slides in here. But now I'm going, how much time do I have?
You were at,
24 minutes.
Yeah.
Oh, fine.
yeah, you're fine.
Okay, so now let's talk about life cycle of stars and where they come from. And I have lifted whole sections of this from my asteroid lecture because the formation is relevant. So, what are stars? Where do they come from? Well, story time. So, stars, right? They're everywhere. They fill the heavens. And you might have seen this. You are here. Well, these bright regions around our galaxy are called star-forming regions. And I didn't even circle all of them. There's a lot of them there. And so, a long time ago in one of these star-forming regions, wind pressure from hot stars, or there's several other different ways it can happen, or supernova shock waves can cause these things to condense and collapse. I love that picture. So yeah, here's an example of a supernova explosion. It can push these things around and cause stars to form in these dense gaseous regions. And here's an example of them. These are baby stars. These are called proplyds. This is in the Orion Nebula. And these are baby stars with their envelope of gas around them. Now this gas in these pretty pictures is mostly hydrogen, a lot of helium, and dust. Well, that dust is a pretty generic term for a lot of different stuff. And something like this. There's a lot of different molecules in the interstellar medium. Now what we've got here is molecules with 2 atoms all the way down to complex ones with 10 or more atoms. And some of these are pretty familiar. What's really interesting are all the organic molecules that has been discovered in the interstellar medium, including glycine, and just recently, that, a key chemical property of life in a very complex organic molecule. Now these things, think in these gas clouds, you've got stars with a lot of energy pouring out, and you've got, it's just a chemical soup in there, and these things can form. So you've got all these molecules, including organics, and stars form out of them. So as these clouds begin to condense, they flatten out, they begin to spin, and the center starts to get hotter. This is called a protoplanetary disk. And here's an example of them. You can see flat disks. And we didn't, this was hypothesized. These are Hubble images, and we didn't have confirmation of this until Hubble went up and saw them. So that temperature in the core of these things gets so hot that nuclear fusion starts, and whoosh, you get a star. And in the remaining gas and dust around there, you get, here's an example. A lot of these baby systems have jets. They're very unstable. You can see the disk of gas there. So this is a baby star just formed. So planets form in these disks, and eventually the wind pressure is going to push that stuff away, and you'll have a solar system like that. So again, to recap, you've got a lot of organic molecules. Stars and planets form out of that. So all those organic molecules were here to begin with. And personally, aside from the size and distance in the universe, I think that this is one of the most important concepts in astronomy. That the organic molecules were already here. So that's really, really cool. So continuing on with that, most stars, they form in clusters, and they drift away from each other over time. The Pleiades is one example of that. Now, the Pleiades, you see this nebulosity around them. That's not actually the nebulosity they formed in. They're traveling through somebody else's nebulosity. That's not related to them. So this is an open cluster, and the stars will eventually drift away from each other. Most of the stars that you see in the sky, most of the stars are binary. A lot of them you can't see, but they seem to be the rule rather than the exception. So there's a very arcane reason coming for that one.
By the way,
Fantasy binary
I'm
stars.
closing my
But
eyes so I do not contaminate my brain.
you guys might have seen that in the sky, the Big Dipper, right?
That's more like it.
Okay, that star right there in the Big Dipper is pretty darn interesting. And by the way, Big Dipper is not a constellation. I had a kid come up to me on a poster where the Big Dipper was labeled as a constellation. He says, "That's an asterism. Where's the Ursa Major?" And I'm looking at it going, this kid's like, "You're right."
Good boy.
Yeah, cool.
Good
You're right,
boy.
kid.
From the mouths of babes.
So, you might be able to resolve with your naked eye the fact that there's two stars there. I used to be able to before I needed glasses, but that actually used to be used as a test. I've heard that it used to be a test for Centurions to get in, but yeah, I know. So anyway, through a small telescope, you actually see more stars. You see the close-up one here, Mizar is 2, and you see another one way out. Well, that's not the entire story there. What you've got here is, that's Alcor. That's Alcor. That is a double star itself.
Right.
Okay, so now we're going to go over to Mizar. This is in Universe Sandbox. This is a really cool app for the PC. So you've got, this is Mizar, and that is a double star, and they orbit around their very center there, their center of gravity. But the interesting thing about this is that being a double star isn't the entire story. So let's zoom in on one of these guys.
Oh, that's crazy.
So it's actually a double. And the other one is a double. So you've got two doubles doing this around each other with Mizar and Alcor. So yeah, that's pretty cool.
Brain is starting to hurt.
So yeah, that's really, really cool. So yeah, double stars are pretty much the rule. Now Mizar and Alcor are optical binaries. They're way away from each other, so they just appear binaries. But the fact that they're binaries themselves is pretty cool. You're not going to go to the next one? There we go. Star types. This is from Universe Sandbox too. I love the way they represent this. These are star types. Our sun is a type G. Most of the stars in the sky are red dwarfs, 76% of them. So our, oops, where'd that go? Hello, stop that. Yeah, our sun, and I stole this from the Bob book. Our sun is bigger than 80% of stars, and that's just amazing. The bigger stars, see the percentages here, are very, very low. And star types, red dwarfs are they're not very hot. Our sun, 5,000 degrees. Now you start getting up into 30,000, those are pretty darn hot stars. So here's an example of star sizing, and this is from the Universe Sandbox. I love this app. This shows a red dwarf compared to our sun, a brown dwarf, and Jupiter. And that's our sun up there. You can't even see the disk, you can see the glow compared to Betelgeuse and Aldebaran. So stars can be very, very big. Largest known star, 1,400 times the size of our sun. And the brightest star, now I had two different conflicting things here. This Universe Today article said 40 million. Wikipedia said 2, but after the first million times as bright as the sun, who cares?
Oh, Wikipedia.
Yeah. This is the HR diagram, and this is a tool that astronomers used for classifying stars. And again, I love this one because it shows that there's a bazillion of the smaller ones and fewer of the ones like our sun. So that's a very good HR diagram. I like that one a lot. I think that was in National Geographic, I'm not sure. So, this video, I hope this thing plays right. I love this guy's accent. This is a play. Give me audio, please.
So way out there in space, there's huge clouds of dust and gas. And if one of those clouds of dust and gas is massive enough, its own gravity causes it to start to collapse. So it falls in on itself, and towards the centre of that cloud, it gets denser and denser, it gets hotter and hotter. And eventually, the particles that the gas and the dust are made of are brought so close together that they start to stick together, they start to fuse. That's the energy source of a star. The star switches on and begins to shine.
Inside every newborn star, hydrogen atoms are fused together to make helium. This process is called fusion, and it creates the energy that powers every star. What happens to a star during the rest of its life depends on how massive it is at its birth.
A star like the Sun is in a delicate balance between gravity, which wants to make the star collapse in on itself, and the pressure that pushes outwards that comes from the energy that's been produced in these fusion reactions happening at its core. However, at some point in the future, the hydrogen runs out, and at that point, the core of the star will start to collapse in on itself under its own weight. It gets denser, it gets hotter, until a point where you can actually start to use the helium atoms themselves as the fuel for the fusion, pushing helium atoms together and making carbon and oxygen the next heavier elements in the periodic table.
As the star begins to fuse helium, it creates more energy, and that causes the outer layers of the star to expand. One day, our sun will grow so large it will swallow up the inner planets of the solar system, out as far as the Earth. It will become a red giant. For the sun, this will be the beginning of the end.
What happens is that the outer layers of the star get farther and farther from the middle. The force of gravity that they feel is getting weaker and weaker. And actually, the star loses hold of its outer atmosphere. Its outer atmosphere drifts off out into space. It expands out to become a planetary nebula. And they're some of the most beautiful objects in the universe.
Once the outer layers have drifted away, all that is left of the star is its core.
A white dwarf star is the dead remnant core of a star like the Sun at the end of its life. What's left behind is something that might weigh as much as half the mass of the Sun, but it's only about the size of the Earth. So it's an incredibly dense object, it's dead, there's no nuclear fusion going on anymore, it's incredibly hot, but then over millions of years it will gradually cool down to become a black dwarf.
Some stars, however, are much more massive than the Sun, and they lead very different lives. They are able to fuse heavier and heavier elements inside their core. The star gets bigger and bigger. Some grow up to 1,000 times the size of our Sun. until it has fused elements all the way up to iron.
And once we form the iron core, there's no more energy can be got from fusion. That core collapses. The rest of the star starts to collapse in after it, but then it bounces off. There's a huge shock wave, and in just a second, bang, the outer parts of the star are blasted off into space in a huge supernova explosion. These supernova explosions are so powerful that when one of these stars explodes, it can actually outshine the whole galaxy of which it's part, a galaxy of maybe 100,000 million stars.
For these supergiant stars, all that is left is the super-dense core, known as a neutron star, an object that can have a mass greater than our Sun, but be less than 20 kilometers across. But for the most massive stars of all, we think when the core collapses, the gravity is so strong, it becomes a black hole, from which not even light can escape.
So stars are actually the places in the universe where the elements are created.
After the Big Bang, our universe contained only hydrogen and helium. All the other heavier elements were therefore fused inside stars.
The amazing thing is that virtually everything you see around you was made inside a star, billions of years ago before the Sun and the planets were formed. And when that star died and blasted its guts out into space, that formed the raw materials from which our Sun, the planet Earth, and indeed ourselves were made. And actually, I think ultimately that's one of the major reasons why I think understanding stars is crucial, because it's actually telling us where we came from.
One of the comments I saw, and this is a YouTube video, one of the comments I saw is, I learned more in this four-minute video than I did in 4 months of an astronomy class.
Oh.
Oops. 10 minutes, Bob.
Okay. So yeah,
There's a lot there.
so again, to recap, here's the life cycle of our Sun. It forms out of one of the star-forming regions, and right now we're in our main sequence, and it's going to stay there for quite some time. Well, eventually, it's going to turn into a red giant. Atmosphere is going to slough off, and you'll have a planetary nebula. So that's it. Here's layers in the Sun. Eventually, you got all this helium that has been created. It sinks to the core, and eventually you'll have this layer structure, and the layer structure is much more pronounced in larger stars. So here's a recap of different stars. Depending on how big they are, you can have different outcomes. Stars can red dwarfs or brown dwarfs will form. They'll just stay brown dwarfs forever. The red dwarfs will burn for what, trillions of years. Stars like our Sun will form planetary nebulas. Larger stars can actually, this is pretty interesting. Blue giant stars, they can actually go into a supernova, slough off something, and go back into main sequence.
Hey, really?
Yep.
It's amazing.
What? Yep. And I read this just recently. Some of these stars can be so big, they just collapse right into a black hole at the end of their life. So yeah, there's a lot of different outcomes depending on the star. And again, an entire lecture could be done just about this alone. Here's some cheerful pictures of the Earth and the red giant phase. I'm glad you're here, Gary. I put this slide in here just for you. This is a supergiant, a variable red supergiant star, and the reason, this is over months and months, and this is the reason it's variable, is because its atmosphere is so turbulent like that.
Yeah.
This is a computer simulation. I thought you'd like that.
Wow.
Beautiful.
Isn't that neat? So yeah, there's white dwarfs as big as the Earth, but mass of about the Sun. So I've actually done this in Universe Sandbox and let that go, and the Earth goes poof. So yeah, that's. So neutron stars, there's Manhattan. They're incredibly dense. These are the things that you hear, like a teaspoon of it weighs millions of tons. And there's the Crab Nebula remnant, and it is spewing out waves of energy into the Crab Nebula. Black holes, these are weird dogs, but they're not magic, all right? So they're stars, or they used to be stars. They're a place where the gravity pulls so much light can't get out. That would be a black hole about 1.5 Earth or solar masses, very, very tiny. I guess the Earth, if the Earth could be made into a black hole, it would be about a centimeter across. But black holes can be supermassive. The cores of galaxies contain million solar mass black holes. There can be stellar mass black holes, about the size up to 20 times the mass of our sun. Quantum black holes are completely theoretical. It's hypothesized, or what's hypothetical. It's hypothesized they could have been created in the Big Bang, but they're the size of an atom. But yeah, there's lots of science fiction on it, and that's about it. So, misconceptions, okay? They don't go around the universe eating stuff. Well, they do, but they're not wanton about it. The Earth is not going to fall into a black hole. I actually had somebody ask me that. There's no black hole around us in the solar system. It's just not going to happen. Even if the sun was magically changed into a black hole, the mass of the sun, all the planets would still orbit it the same. We wouldn't care. So the sun is not going to turn into a black hole. It's not big enough to do that. And the black holes have been portrayed in the theaters very badly. And so the black hole, this is the core of our galaxy. And what these are stars orbiting something unseen in the core of our galaxy. Over the course of what, several years here. These are stars moving like that. That is just amazing. So again, most stars in the skies are binaries. Sometimes these binaries, you'll have one of them turn into a black hole. What you're seeing here is a black hole pulling material from a blue giant binary. And Dave Bailey actually talked about this a couple of years ago. He really likes seeing this because of the point where all this stuff reaches the accretion disk, there's fusion going on there, that one little spot, the hot spot. So, so I would like to invite anybody to present for the W.A.S. There's tons of things I had in this lecture that could be 1-hour lectures in their own right. And it's really great being up here speaking to you guys. I really like it. So thank you all and enjoy the evening.
And thank you for speaking.
I have an answer for the question about IBEX.
Pardon me?
I have an answer to the question about IBEX.
IBEX?
It is in a high Earth orbit, highly elliptical, whose semi-major axis is 100,000 miles.
All right.
Perigee 55 miles, apogee 250 miles. 250,000.
Yeah.
Holy smokes.
So, sorry, 50,000 miles, 250,000 miles.
So, like
Alright.
the moon then.
Yeah.
Actually, they changed,
Moon.
so they changed the orbit of it to save power because they were getting too close to the moon, and they had to adjust to move to the moon, and it was using up fuel a lot.
Yeah, I
faster
can
than they
imagine.
wanted.
That would be every few months, so
Yeah.
you'd have to tweak it.
So we do have time for a couple of questions, if anybody has any
Yeah.
questions for Bob.
Yeah, I got, well, maybe you can add to this, Bob.
Yes.
I've heard recently from a fairly reliable source, old drinking buddy, that the reason that globular clusters, especially M13, have streamers, which is anti-intuitive, is that M13 and M22 can have at least one black hole in there, and that's kicking the stars out in these erratic-looking streamers or swirls.
Wow.
Have you heard anything like this?
I've heard some things. Black holes in globular clusters are exceedingly rare from what I've heard, but they're not unheard of.
All right, this is not some outrageous thing, but so in other words, because what Mark John Christensen said is that M13, I don't know where he gets this, could have 3, 4, 5 black holes in it. Does this strike you as reasonable?
Well, how many type O, A, or B stars could have been in there?
Not very many.
Any?
Yeah. All right. Point taken. So you're saying that the precursors for the black holes in the globulars don't exist, and so you can't have a lot of them in a globular cluster.
Well, it depends on if you're doing a type 1 or a type 2. If you've got a binary system with a sufficient imbalance, you could pull off a type 2, type 1A. Type 1A supernova.
All right, I've never heard of a supernova being observed anywhere in a globular cluster.
Me either,
I will
but
look it up for you, Gary.
All right, well, I mean, don't rush right out, and, all right. I mean,
okay, for one thing, we're not entirely sure that globular clusters are not all stripped-down galactic cores. If they're stripped-down galactic core, then there is likely to be a black hole lurking in the center of one.
all right, well, I converted to Christianity, so I don't believe that. All right. All right, point taken.
Any additional questions?
Yeah, I've got one. During the video, it was talking about the larger stars than our sun. They go through fusion and produce atoms up to iron.
Yeah.
But we have other, more heavier elements than iron. Where do those come from?
Supernova explosions.
Supernovas, you have the energy required to fuse something up into those higher elements is ridiculous. Well, that ridiculous is provided to you. So you've got isotopes and ions smacking into each other all over the place, and they're going to have any number of protons and neutrons and stuff, and supernovas literally create every other element in the periodic table, although I've heard something about merging neutron stars are responsible for gold. I'm a little on that.
Well,
Yeah.
uranium would be heavier.
The stuff will naturally
So, yeah.
fuse up to iron, but then beyond that, you need something to add energy in. 'Cause
Mhm.
it gives up energy fusing up to iron, but then you need something to add it. So
And then that
supernovas
supernova explosion
will
gives you
plow
all
pieces
the
together or plow neutrons into and protons into another existing, so then they can bump it up the ladder. Until it gets to the unstable range, then it starts bumping back down again.
That's right.
So what is the genesis of a supernova? I thought it was still a star that went supernova.
But in that explosion that's going on as a supernova, that's where the outer layers plow in and can create these higher elements.
Okay.
And then
okay.
spread them out also.
So as time goes by, the dust that the stars are forming out of has more and more impurities in it as you're basically endlessly recycling.
Sure.
Okay,
The early tape was really boring with just hydrogen and helium, so we started to litter it up.
yeah.
Right, right.
Right.
So unfortunately, we have to get out of here, so let's give Bob another round of applause.